right. Welcome. Hold on, I've got a cable that's not moving. Just a second. Okay. That should be a little better. Okay. Something like that, maybe. Okay, so I will be showing you stuff on Zoom, on the YouTube stream, so you may want to jump over there, but as always, you're welcome to consume these in whatever manner works for you. It's just you'll miss a lot of what I'm trying to show you if you can't see the background like we have in the Zoom meeting. So I'll wait a little longer to take roll. Imagine we'll get a few more people rolling in. Let's see, this was an online class, so we don't have to worry for this class about our return to campus next week. So that is as of the 14th. If you're in a class that is scheduled to meet on campus, they will start meeting on the 14th. So just be prepared for that. I expect it's probably going to be, right. It's probably going to be a little chaotic that first day, usually is. Maybe not as much because we have so many more online classes than we used to. I don't know how they're handling the details of the students needing to get their pass done for that first day. I imagine it's going to be nuts. I imagine a lot of people are going to show up to class that first day. Screening people say, sorry, you can't get through unless we've approved your vaccine. People trying to do that in the parking lot, not likely to work. So I would take care of that stuff sooner rather than later, but this is a Zoom class, so we don't need to worry about that. That's for your other classes. So, however, what we do need to do, because we are an online class, one of the requirements, and I'm oversimplifying a bit here, but most of you probably don't care about the actual details. But the bottom line is, again, oversimplifying, if we're doing an online class, I am supposed to be putting up graded discussions. There's supposed to be discussion among students, and then of course I have to grade them or no one will do them. So if we go here, you will see now at the end of our first chapter here that we are wrapping up, there is a graded class discussion. Okay, so you have till February 14th to be part of that discussion. If you go in and you leave a meaningful comment, then you will get credit. So there's already some comments in here, so that's great. You can read other people's comments. In fact, that's kind of the point, is to read other people's comments, right? If you don't want to always just view classes as how do I just get the points I want so I can get my 70% and get out of here? You're trying to grow and learn and become a stronger person. So, a lot of that is reading what other people have to say, listening to what other people have to say, have the whole conversation. So there's a discussion in here. We will have numerous of these. I don't know if we'll have one after every module, but we'll have them fairly frequently. It's part of our the requirement at the college for online classes because it's actually part of accreditation, and accreditation is coming next year, and we have to be able to show them. They're going to look back at our courses. It's like an audit. They go back and look at the courses for the last few years and randomly select them. And if it's an online class, they're going to want to see discussions on here. So, plus they're a good idea, right? They're also helpful. So I've got a graded class discussion on here. You will get 10 points for that. This will go in the same homework categories. So honestly, it's a pretty easy homework assignment, basically. So what do? Number 1, please leave a meaningful comment below. Okay, meaningful comment. So you can't just come in here and say, oh, good comment, and then think you're going to get 10 points for that. Or I agree with you and get 10 points. You can say those things. That's totally fine. If you want to tell someone you really like their comment, go ahead, but you're not going to get points for doing that, right? You like basically the way you want to think about it is if someone took your comment or question away, would it change the discussion? So if you ask a good question and we take that question away, then yeah, there will be something missing now because we've taken your question away. Or if someone's having trouble and you make a suggestion and say, oh, I know one thing that might help you with that, and then you give them a suggestion, that's helpful. That is moving the conversation forward, right? But if you go in and say something essentially meaningless, like, oh, I agree, or good point, if we take away your comment of I agree, is the conversation any worse? No, it's the same because your comment was essentially an empty comment, right? So when you're trying to figure out, well, what do I need to do to receive credit for this assignment? Make a meaningful comment. So that's either asking a question or giving someone a response to their question that is, really meaningfully valid, where, and I don't mean it has to be like life-changing, but like, if someone's saying they're having trouble using the graphing utility on Delta Math and you explain to them how to do it, you just helped that person, right? That was helpful to someone. So make sure it's a meaningful comment or question. No low-effort comments like I agree or you make a good point. Again, you can write those, but you want to write another one that's going to get you your 10 points, okay, that's like more meaningful. Your comment should further the conversation in some way. You can do this by leaving a new comment of your own or by leaving a helpful or meaningful response to someone else's comment/question. The topic should address one of the following. Really, you want to address all three. It's kind of one big topic, but I just gave you some questions to sort of make things progress. So, what is the biggest challenge so far in this class? What are you having the most trouble with? What is the most difficult thing for you? Is it the technology? Is it using the graphing tool on Delta Math? Is it keeping up with the homework and staying disciplined to keep doing it as you go? Is it the technology that like you have trouble doing this from your computer at home, or you're having trouble because this is a fully online class and sometimes when you have a question, you can't just turn to the person next to you and go, hey, looks like you did number 7. I'm kind of stuck on number 7. Would you mind explaining to me that thing there? Which is something that's like trivially easy in class for most people. Some people have difficulties that get in the way of that. But for most people, you just, especially if you've been friendly with a couple people in the class, you just go, can you help me with this? Well, in this scenario, you can't do that, right? So many different ways that challenges can come up. Maybe work just doubled your hours last week. Well, that's going to make it harder for you to do your homework, right? So challenges in the class so far. What ways have you found to overcome some difficulties in this class? Have you found that maybe this is the first semester where you decided to make yourself a schedule, right? A lot of people are just like, I don't know, I'll just wait around, and then when something's due in one of my classes, I'll start working on it like a couple hours ahead of time before it's due. That's what a lot of students do. That's a very poor strategy for being successful as a student. But, maybe you put yourself on a schedule and said, okay, here's when I work, here's when I got family obligations, here's the times when I can study, and if I stick to this every day, I'll stay current and I won't get behind on the homework. Different things. Some people switch to a laptop and then they're like, yeah, because then I always have my computer with me, and then whenever I'm stuck somewhere for 45 minutes, I can just take out my laptop and I can do some of my work or whatever, right? So something that you found helpful, that's another thing you can discuss. And what study skills, technology, habits, etc. have you used to make this class easier for you? So all three of these are really one big topic, right? So you don't necessarily have to address all three specifically. They're kind of one big thing, and you just want to get this out of the way so that, it's entirely possible that something you have found that is now helping you be more successful in the class will help someone else, and someone else will go, oh, I never really thought about like ways to keep myself disciplined about doing my homework, but this woman has a really good suggestion about how she's keeping herself. She was able to develop a habit of keeping herself doing the homework regularly. I'm going to try what she's doing, right? That's the kind of stuff that can be helpful to each other. And it kind of takes the place of, honestly, when I'm in the classroom, I hear a lot of conversations before and after class. And of course, some of them are silly and just getting to know each other and stuff. But some of them are, about the class. And they're like, I can't get this graph to work right. And then someone's like, no, you have to click this point, and then you have to click the ends to get the right end. And then the person gets it, right? So So we miss some of that in being an online class. We miss some of that being able to interact with each other, because the reality is probably everyone in this room knows a couple things that were obvious to them about this class that other people in the class like are dumbfounded by. They're like, I don't get how to do this thing. And if you guys like you do in class where you chat before class, you could all help each other and sort of work it out. But we lose that when we're online. So that's really all this is. Chance to, talk about some of the things that have worked for you. What are your biggest challenges? How are you working around those challenges? That kind of stuff. Okay. So you have till the 14th to do that. That's due on the 14th. Make sure you get it done by then, right? And these assignments where like you have a week, don't really extend them because you have a week. So I'm definitely seeing more of this in my classes where like in some of my classes, and you can see this on the other homework assignments, you got 2-3 weeks to do an assignment, and then the last night that something's due, somebody's like, oh, I don't feel good, I can't do the homework tonight. It's like, well, you had 3 weeks to do it. Like if you're waiting till the last hours and then something goes wrong, that's really on you, right? That's one of the that's a study skill that is extremely important. That's a skill that carries over into work as well. If your boss gives you a job and he wants it done, he wants a project done in 3 weeks, and you had 3 weeks to do it, and then you go in there the day after it's due and you're like, sorry, boss, I got food poisoning last night. Like, you're not going to be in good standing, right? So, just kind of think about that stuff and leave a comment in here. Okay, so with that said, where are we? Okay, I got class meeting, syllabus, homework. We don't have to worry about being back in the classroom. Right, so we're going to move ahead with stuff. So the rational expressions and the rational equations, if there are specific questions, I'm happy to answer those, and we can certainly go over them in office hours as well. So if you have, like, if people send me questions, like by Wednesday, I'm happy to go over those on Wednesday. But the thing is about that is that, the rational expressions, so that is rational expressions and rational equations, those sections, pretty much what I'm going to show you in class would just be, if I was going to show you those problems, it basically would just be repeating the videos. Like, there's really not anything more to talk about. I think it's covered pretty good in the videos. And the other thing is, it's actually really hard to do the, as you can imagine, fractions of polynomials, to get the math type to do it right, where it sets it all correctly. Like it's hard to do it fast, like on the fly, where I'm showing examples. So, and like I say, I wouldn't really be able to do much that isn't in the examples. So watch the videos on the homework problems, watch the videos that I have posted on here, and I think you're pretty much going to be good to go, right? You'll be able to figure those out. And if not, send me questions and we can talk about it Wednesday. Oh, wait, I'm sorry. I'm thinking of my Monday, Wednesday class. This class is just once a week. Those homeworks are due the 14th. So we'll actually still have next Monday to talk about it. So if people send me questions on this material, like send me a specific question. Don't just go, oh, can you go over rational equations? Like send me a specific problem or something that you're working on. And we can still talk about it Monday. And those homeworks are due Monday. Okay, so we'll still talk about that. So otherwise, I'm going to move ahead with stuff that I think is more productive to talk about in person rather than a rational expressions where you really should just watch the videos and get it. Some of the stuff we're going to talk about makes more sense where I can give a full rounded explanation of things, and I think that's a little bit more productive. So I'm going to move ahead to the systems of equations. Let's see, do I have that released? I don't. Let me release that right now. Okay, so that should be published for you now. We got the green bar, there we go. And I think all of these, I think I populated videos and all of those. Yep, there we go. So plenty of videos for you to watch for systems of equations, and we can talk about it, okay? So, right. Okay, so systems of equations, we go into Delta Math. So you've got homework assignments on this. And remember, your Delta Math is really graded on completion, so you always have the ability to get 100% on these assignments. You just have to keep working on them. Well, up until the due date, and then any problems you do after the due date, you get half credit, right? So be careful about that. Okay, so let's take a look at solve linear systems graphically. That's what we're getting into first. So what are systems of equations? Well, an equation, we know what that means, right? And we kind of talked about that last week. In fact, that will be part of what you're doing in the rational expressions and equations homework, is answering the question of what is the difference between an expression and an equation? Like, what is that? Do I know what an expression is? Do I know what an equation is? Like, sometimes a lot of people call things equations in mathematics that aren't really equations. They just kind of mean, like, I don't know, it looks like some math stuff, so I'm going to call that an equation. The main way that you can tell the difference between an expression and equation, and this is assuming that it makes sense, right? Just like you can take words and capital and a period and punctuation, and you can just put random words up there and it looks like a sentence until you go to read it and you go, wait, these are just random words, right? Well, you could do the same with math. You could just put up symbols and numbers, and first someone goes, that looks like math, and then when you look closer, you're like, actually that's not right. So I'm assuming we're talking about something that makes sense mathematically, right? I mean, that's not just like random symbols and letters that are math symbols. It's something that has really has a meaning to it. Then what is the difference between an expression and an equation? Well, an equation is pretty easy to spot because an equation has an equal sign in it. Okay? So it is equating one thing to something else. An equation. Equation, equal sign. The equa part is sort of connecting it. Equal sign and equation. So if it doesn't have an equal sign in it, it is not an equation. Okay? If it has an equal sign in it, and again, we're assuming that we're talking about like legitimately defined stuff, then it's an equation. So what is an expression then? An expression is a mathematical object that doesn't have an equation in it, right? And there's lots more mathematical objects you'll get to later in mathematics, or some of you will, depending on what math classes you take. But for now, just that's kind of the main distinction. Is there an equal sign in it? Yes, then it's an equation. Is there an equal sign in it? No, then it's an expression. Okay. Now, why is it so important that we know the difference between an equal sign, an equation, and an expression? Well, it's because we use different mathematical tools on different things. So, for instance, if we have an equation, then we've had a rule since beginning algebra that says if I have an equation, then I can add 5 to both sides of that equation, right? We can take whatever number we want and add it to both sides, but I'll just say 5. I want to add 5 to both sides of this equation, and that is a totally legitimate mathematical step for me to take. But I can't add 5 to both sides of an equation if it's not an equation, right? If there's no equal sign, then how do I add 5 on the left and the right of the equal sign? And the answer is you don't. And that might sound ridiculous, right? You might be going like, why would someone try to add 5 to both sides of an equation that isn't even an equation? I can tell you, I see it all the time. Okay, students do it a lot. That's why I'm covering this topic, is because I see students try to do things when they treat it like it's an expression, when it's really an equation, and I see people try to do things to an expression and they're treating it like it's an equation. You have to understand the difference between those two. Pretty easy to do. Is there an equal sign? Yes or no? And then you know which one you're dealing with. And then you can decide, oh, well, I know that I can multiply both sides of my equation by 1/2, so I'm going to do that. Once you know you have an equation, then you can use those tools. Can't do that if you have an expression. Okay, so it's really important to know the difference between an expression and an equation. So now that we kind of know what an equation is, right, there's a bunch of like stuff we need to remind ourselves about before we get into actually where I'm going. So it may seem like there's a huge amount of buildup before I answer the question of what is the systems of equations, but that's because otherwise you're going to be asking these questions in a few minutes, so I might as well just get them out of the way now, right? Okay, so then we have this idea of an equation. All right, so now I'm going to go to Desmos. I think I've showed you this in class. Desmos, it's D-E-S-M-O-S, Desmos, D-E-S-M-O-S, is a free website. It's got a nice graphing tool on it, very easy to use. Don't be afraid to come here. You don't have to make an account to use it. You only have to make an account if you're like a teacher like me, where I've constructed some pretty advanced stuff in here for mainly for calculus classes. That I don't want to have to remake. You know, if it takes me 15 minutes to make it, I don't want to remake it every time I teach that class, so you can save it. But for most of you, you don't really care. You don't have to even make an account. Just go right in and click graphing calculator. Okay, so we want to remember, what is an equation then? So let's remember, because if we really understand what an equation is, systems of equations is going to be a whole lot easier. Right? So this is that part where I kind of always hit on this. We want to understand what's going on. We do not want to memorize. Now, yes, in mathematics, there's always at least a small amount of memorization because you have to remember certain things, right? But this is one of those topics where I see people trying to memorize things instead of thinking their way through it, and it totally messes them up. Right? I can tell you, as someone who has graded thousands and thousands of algebra tests, I can tell when people have tried to memorize stuff and then they get confused and they're doing a bunch of stuff that doesn't make any sense. But when you look at it from the lens of they've tried to memorize this and then they made this one mistake and then it's all messed up after that, you really want to understand it. No, basically, if you don't understand what's going on, none of this stuff's going to be useful. Right? You're not really going to even understand what you're doing. And considering the importance of what we're covering in the second half of this class, literally lives are in the balance. Most of my job, most of the classes I teach, like lives don't hang in the balance. But for many of you, the futures, your futures, people's lives will hang in the balance. So it's really important that we have a good, solid understanding of what's going on, right? Plus liability for yourself, right? Your liability as an individual, and then the safety and health of other individuals. This is pretty important stuff we're talking about, right? So we want to understand what's going on. So let's take an example. What is a linear equation? You can have systems of equations that are nonlinear, but I think if I remember correctly, we only cover linear equations in this class, right? Well, systems of linear equations, I should say. So a linear equation might look like, remember the y equals mx plus b? So let's look at that. Y equals negative 2/3 x plus 1. And it graphs that line for me pretty nicely, right? So what is that line really, though? Like, what does that line really represent? I see an equation and I see a red line on my graph, but like, what am I looking at? Well, it's easy to think of that line as some solid object, like a bar or a pole or something like that. Like you could pick it up and swing it around and do some kind of cool stuff with it. But it's kind of not. I mean, it doesn't really matter if it's not really solid or not, because it's just sort of an imaginary object. But if you think about it, it's not really solid in the sense that it's really just made up of a bunch of points that are kind of together, right? It's a bunch of little tiny dots that are so close together it looks like a solid object. But what this line really is a collection of points. So what kind of points is this line? The points are all solutions to the equation that the line represents. That equation is y equals negative 2/3 x plus 1. So what does that mean? That a point on this line is a solution to this equation? What's that mean? Well, we have two variables, an x and a y. Generally, our x is horizontal and our y is vertical. So if I take any given point on this line, let's take one that looks nice, for example, one that's going to show up. Let's go with, let's take the point negative 6, 5. There we go. So we can see that point. Oh, I can make this better, I think. There we go. That looks a little better. So we've got the point negative 6, 5. So remember, on graphs, you move horizontally first, vertically second. So negative 6, 5, I go in the negative direction horizontally, 6 units, up 5. That's the positive direction. It puts me on this point right here. Well, that means that my x is negative 6 and my 5 is my y. So if I plug these values in, this would be 5 equals negative 2/3 times negative 6 plus 1. Okay, so let's think about that. If I plug negative 6 in here, I would get 12/3, which would be 4. 4 plus 1 is 5, and that's what we would get over here. So basically this solution means if I plug the 5 in for y and the negative 6 in for x, I get a true statement up here. That's what a solution is it's a collection of coordinates that satisfies this equation. Okay? Every point on this line satisfies this equation. If we pick another point over here, say 0, 1. So I pick another point on the line. So I plug in 0 for x and 1 for y. We can see pretty quickly this becomes 0 and it becomes y equals 1. Yep, that works. We'd get 1 equals 1. So any point we pick on this line will satisfy this equation. So all a graph is, I think a lot of times people memorize a graph and they never even really get to understanding the point. Why do I graph something? It is a visual representation of the solutions to an equation so that you can see things like, well, is it going up? Is it increasing? Is our profit increasing? Is our profit decreasing? What's going on here? We graph it to see all those points and try to understand some kind of behavior. Okay. So that's what a line is. It's just a collection of solutions to that equation. So now, in fact, right before we do that, let me see. Let's get roll out of the way. So give me a minute here. This is really great with everyone putting their stuff in there so I don't have to ask and we can get right to it. So let's see. But this is a pretty full class, so give me a minute here. Okay, so, and I might have missed some names, but let's see. So, according to my record, I'm missing, nope, that person's here. Oh, whoops, I'm in the wrong column there, no wonder. Let's see. I think she emailed me. Leave a note there. Carly D. Maritza D. Esmeralda E. Allison F. Giselle L. I thought this, didn't I see this person? Yeah, this person here is here. Catherine N. This person emailed me. And Soila T and Melanie Z. Let's see, we had a couple people here. Let's see. Oh. Okay, so we got this person. This person. Oh, I had Jocelyn down. I don't know why I said that name. And then okay. Thanks to the people who just sent me text. And then let's see, and then Giselle L. There we go. Okay, thanks. I believe I've got it updated from all the people that just gave me their names, so we're good to go. Remember, it's important. Honestly, at the end of the semester, when I'm giving out grades and I see a grade that's like real close, like, and I'm not saying, like, some people are like, oh, well, I'm like 3%. Isn't that really close? No, that's not close at all. But if you have a grade that's like really close to the cutoff, you know, what I usually do is go back and look at that person's work and figure out, like, okay, because, you know, we don't give plus or minuses at this school. So it's a big difference between like a B and a C, right? You know, or an A and a B, right? So if it's so if it's close, what I usually do is go back and I look at the person's homework and attendance. And if the person was attending regularly and the person has a high homework score, then I'm more likely to bump that person up that tiny little sliver, right? And everyone has a different vision. Like I say, people are like, oh, I got like a 77. Doesn't that mean I should get a B? No, I mean close, like real close. But if the homework has been done and the attendance is good, then a lot of times I'll give the benefit of the doubt and bump that person up to, you know, to that next grade level. I don't ever like give someone else a grade above someone else because of that. Like if someone gets bumped, everyone above them will get bumped up as well. But that usually it's like one person that just missed the cutoff. But if I'm wondering like, ooh, this person got like a 69.7 and I have to make the decision whether that person has to take the class again, I go back and look and go, oh, well, he didn't really do his homework and he didn't really come to class. Why does he deserve like a benefit, like a bonus, right? In general, like, you know, should have showed up a little bit more. And if you had done some homework, probably wouldn't ended up with a 69.7. You'd probably be in the 70s if you had done the homework. So in those cases, people don't usually get bumped up. But if it's clear that the person really put the effort into the course, sometimes I'm not putting myself in. I'm not like my options are open. I'm not limiting myself. I'm just saying that's a thing I look at when I'm deciding should a person get bumped up to the next thing. Okay, so we got that taken care of. Oh, right. So we just reviewed lines, right? So remember, what did we just decide? A line is really just a visual representation of the infinite number of solutions to this equation right here. There's an infinite number of points. And there's an infinite number of points between any 2 points, right? Every one of us in the class could pick a different point between these 2 points, and they would all work in this equation right here. So the coordinates of a point are solutions to that equation. So what is a system of equations, right? I've taken a long time to kind of come full circle to talk about what we're talking about. Well, a system of equations is when you have more than one equation that has to be satisfied at the same time, right? This happens all the time in life, in our everyday life. We have like a couple things that we need to accomplish, but they have to be accomplished under a certain set of circumstances, right? So we have to do things a certain way. So we want to figure out, well, is there a way that I can take 2 equations and find out if there's a solution that satisfies both of those equations? And that's what a system of equations is. So usually, like here in the beginning, when we start, we're going to be talking about 2 equations with 2 variables. So this right here, this is 1 equation and 1 variable. You did that in beginning algebra. You dealt with 1 equation in 1 variable, and you did different stuff with it. Here we're going to have 2 equations with 2 variables. You can get into 3 equations with 3 variables, and we have to cover it very briefly, although I don't usually put 3 equations and 3 variables on a test, especially not in an algebra test. I think it's a little bit overkill. But we have to figure out how to go through and do those kinds of equations. You can do huge equations, right? I remember when I was in my undergraduate work and my advisor was talking about how when he was in grad school, he had to do, he had a system of equations he had to solve that was like 100 equations and 100 variables. And literally that's what he did for 1 semester, was solve this entire system of equations. Now we just put it in a computer and have a computer do it. When I was in grad school, I had a program running that was solving these specific sets of systems of equations that have thousands of equations and thousands of variables. And then it was solving them, sometimes it would take 4 or 5 days for it to come up with a solution, but then it would go through and it would spit out the answer. We're not going to be doing any of that level stuff, but you should know systems of equations come in all sizes. And there are sometimes consequences to those sizes, but we'll get into all that kind of stuff as we go. So it seems weird, like, wait, I'm going to have a solution that's supposed to satisfy 2 equations? How's that supposed to work? So let's just make one up. It's not coming out how I wanted. Let's do this. I'll be a little less tricky here. Sorry, the one I wanted to do didn't. Here we go. This one works good. Okay, so now I have 2 equations, and we want to know if there's any solutions that satisfy both of these equations, right? Because we just said, well, by the reasoning from a minute ago, every point on this red line is a solution to this first equation right here. Okay, by the same reasoning, every point on this purple line is a solution to this equation right here. So if I'm looking for solutions to both of these, in other words, I'm looking for a solution to the system of equations, then what I'm really looking for is a point that lies on both of these lines. And we have a term for that. It's called the intersection point. It's where these lines meet. So where these lines meet together, if there's a point on both lines, that means that point is a solution to the red equation, and it's also a solution to the purple equation. So we start off, here's kind of the thing. We start off talking about systems of equations graphically because it's the easiest way to conceptually understand systems of equations. Unfortunately, in the real world, we don't usually solve systems of equations graphically because it's kind of an inexact tool. So we use it in the beginning because it helps us get that understanding that we need for systems of equations. And then later we're going to switch over to algebraic ways of solving these. But the algebraic ways, it's really easy to lose track of what you're really doing, right? So we want to have that full picture. We want to understand conceptually what's going on, but we also want to be able to do the algebra of solving these equations. There are specifically some points, I mean, the whole thing I see people memorize, but there are some points where I see people trying to memorize what to do, and they just end up confusing themselves. So it's much better to understand what's happening. So this point of intersection should be a solution to both. And sure enough, if I plug in 0, 1, I get y equals 0 plus 1. Yeah, that's true. What about down here? 1 equals 0 plus 1. That's true. Here we'd get 1 equals 0 plus 1. That's true. So yeah, the solution of an x being 0 and the y being 1 is a solution to both of these equations right here. Okay, so therefore we have found the solution to this system of equations. And systems of equations are hugely, hugely important. Like when I was first learning systems of equations, I just kind of learned it and went, okay, that's kind of neat. And when a teacher asks a question, I know how to answer it now, so that's good. But I didn't really get the importance. The importance of systems of equations cannot be understated. Every area of research out there, every subject to study that involves math in any kind of way, every business out there, there are systems of equations being used in that subject somewhere, right? To do research, to run a business, to do whatever. And certainly there are many more places where systems of equations should be getting used, but people don't really remember systems of equations, and then they don't run their business as efficiently as they could, right? If you take like our business calculus class, which we call applied calculus, we do all sorts of that stuff. We look at price supply curves and where they meet price demand curves, and all this kind of stuff to figure out. It's basically this. It's this problem, except you're looking at a profit or a supply demand and a price demand, and you're figuring out that intersection point has some kind of real world meaning, which sometimes is like, well, this is where you should price your item. This is where you'll sell the most units and still make a good profit. So really important. So why don't we just always do this? It seems easy. I'll just come to Desmos every time that I have a system of equations, and I'll graph it, and then I'll just look at the point of intersection. That seems easy. Why don't we just do that? And the answer is, if I change this just slightly to this, so yeah, the intersection point is now happening inside of a grid line. And in fact, Desmos is trying to give us a rounded decimal representation of the answer, and that looks really exact. Sometimes people look at that and go, man, that's exact. It's actually not. It's rounding off some values for us, and that might seem like it's good enough, but it's not. It just isn't, right? If you're trying to maximize profit, you don't want to be like kind of maximizing profit. You don't want to go, well, we're close to doing the best we can. If you're running a business, you want to do the best you can, partially because businesses tend to fail, but also because if you're going through the trouble of work, why not try to get the most out of it that you can? You want to maximize that amount. So these rounded off values, not good enough. Okay? And they'll make a bigger difference than you think. Like there are certain situations where you might go, well, that's 3 decimal places. Isn't that pretty precise? Well, if the unit you're using is millions of dollars, then no, that's not very precise at all, right? So that's the drawback and the weakness of solving systems using the graphing method, is that they're inexact. So let's take a look at what this looks like in the homework. So here we have solving a linear system graphically. Okay. So we go in there. Remember, there's a video. Watch the video, get help. But you are going to have to remember how to graph lines. You're going to have to remember how to do that. Okay. And if not, you review it and get some help with it. Okay, so plot 2 lines by clicking the graph. Click a line to delete it. Sometimes I get emails. How do I delete a line? Make sure you're reading the directions. It sounds silly. I know sometimes when I say like read the directions, like people think that's like snarky or something. It's not. Like I'm literally like probably 40-50% of you don't read directions. Like if you read the directions, you'll have a much better understanding of what's going on. So plot 2 lines by clicking the graph. Okay, so let's just worry about the first one first. So this is in slope-intercept form. It has an intercept of -7 and a slope of -5/2. Now remember, when you have a negative slope, you can choose whether that negative goes in the top or whether it goes in the bottom. The key is that it has to go in one and not the other, and then you just think about it as rise over run. Okay, so our intercept is -7. So that means that one of the points on my graph is 0, -7. So I've got it there. So see how when I clicked it, it's saying that's one point of your line. Where's the other one? Well, if our slope is -5 over 2, that's rise over run. So I could go down 5, 1, 2, 3. Uh-oh, I'm out of room. I can't really go down 5 and over 2, can I? Because I'm off the graph. So then what I should do is, instead of thinking of this as -5 over +2, why don't I think of it as +5 over -2? That's legitimate, right? Okay, so let's do that. That means I'm going to go up 5, 1, 2, 3, 4, 5, and back 2. So there's one of my lines. So you just plot the points there. If you want, you could make a table, and you could solve it that way, where you pick some x values, graph the corresponding y values. You know, you learned in your beginning algebra class, there's like 3 major ways of graphing lines, and I honestly don't care which way you do it. If you do it like I did first, where you understand slope-intercept form and you graph it that way, that's great. If you make yourself an xy table and plot some points, that works, right? Whatever works for you. Okay, going to this second one, we have a y-intercept of -1. Okay, that's right here. And my slope is 1 over 2. That's my rise over run. So that means I go up 1 over 2. And there's my 2 lines now. And we said that the intersection point of the 2 lines is the solution to the system of equations. So my solution should be -2, -2. Okay. So I go down here, and I'm just going to enter it, -2, comma, -2. Submit my answer. It says, are you sure? Yeah, I'm pretty sure. Yep, there we go. We got it. Okay. So that's how you do that type of problem. Nothing fancy or weird going on there. Let's look at, I forget what level 2 is. Level 2, I think, is just where it's not in y equals mx plus b form. So graph it however you want. Some people graph it with intercepts, lots of different stuff. So let's do this one. For this, I would go to -1, so 0, -1. And then what is this? There's no number in front of my x. What is my slope supposed to be? Well, remember, x is really the same as 1x. If you have an apple, you have 1 apple. But a lot of times we don't say 1 when it's understood that we're talking about 1. So if I say, hey, I have an apple, you're not going to say, how many? I just said I have an apple. That generally means 1 apple, right? It's the same with x. If we write x, that means there is 1x. So 1, written as a fraction, can be written as 1 over 1. So my rise is 1, my run is 1. So if I start here, I go up 1 over 1. There's our first line. What about this? How would you do this? Well, what if we plug in 0 for x? If I plug in 0 for x, that makes my y -5. So that's 0, -5. What if I plug in 0 for y? That makes x -15. That's not going to work because I'm out of room here. So let's see if we make x -9, then that makes y -2. Right? Basically, I'm just plugging in points. Remember where you make a table, an xy table, you pick some x values, you plug it in, you get the y value. So this tells me the intersection point should be here at -3, -4 if I didn't mess it up. Nope, I didn't mess it up. So here we go. Right, and again, there's always the video that you can watch and get some help along the way when you're doing that, okay? So that's how those work. Just graph the lines. See where they intersect. Okay. Okay, then you're going to have some homework about writing systems of equations from context. Now, this is not necessarily easy. It takes critical thinking. Now, after you've done a few of these, you're going to get better at it because you're going to go, oh, this is kind of how these problems work. But in general, writing the equations for a system of equations or writing the equation for any kind of description, it takes critical thinking. You cannot memorize, oh, well, whenever I see this exact type of problem, then my x is this and my y is this. Every problem is a little bit different, okay? So let's work through this one. A company produces fruity drinks that contain a percentage of real fruit juice. Drink A contains 20% real fruit juice and drink B contains 15% real fruit juice. The company used 100.5 liters of real fruit juice to make 30 more liters of drink A than liters of drink B. Write a system of equations that could be used to determine the number of liters of drink A made and the number of liters of drink B made. Define the variables that you use to write your system. Okay, that was a whole lot of stuff, right? I just had a whole bunch, and if you're like, you lost me like halfway through, totally reasonable, because there's a lot of information here. So that's kind of step one, is accepting the fact that, you know, some people are like, well, I read it from the first letter to the last. So I read it, like, okay, your brain may have recognized those words, but until you understand it, you haven't really done what you need to do. You need to keep reading until the problem makes sense to you, until you could describe it to someone else. If someone, you know, walked in the room, you're working on homework, and your mom walks in, or friend or somebody, and says like, oh, what's this problem about? And you go, well, there's this company, and they make fruit juice, and they've got like a unhealthy one and like a really unhealthy one, and they made a total of 100.5 liters, and you know, one of the drinks is 30 more liters than the other, and you know, then you understand what's going on. But like, that'll happen a lot, where I'll get a question where someone's like, I don't understand what they're talking about. It's like, well, did you read it? Yeah, I read it once. You probably got to read it a couple times. When I'm doing these, I usually have to read them a couple times, because it's mathematics in writing is not like history, right? Like, you can open a history textbook and just read it. It's like read a novel, or you just kind of read through it and you're like, oh, okay, so then, like, you know, here's what happened in the civil rights movement. And you're just kind of like reading about what happened. In mathematics, you can't just open a book and like read page after page. Like, you have to stop and think about it and compare to your work and wait, what does this definition mean? And you go back a couple pages and look it up. Math can't be read that way. You got to slow down. You got to reread. Okay. So then when you break things down, this is hugely important, defining the variables. And it's so counter to doing math well, right? And so part of it is, oftentimes students want to skip steps because they're like, well, if I have to write this step out, it's just going to take me extra time. This step of defining your variables will save you time by writing it out, okay? I see it all the time, and I have students that I can't get them to write it out. Once they start writing it out, all of a sudden they're doing significantly better. They'll say, oh, well, what are my equations? And I'll say, well, what are your variables? I don't know. I mean, that's like, you know, you're at a house trying to build a site, trying to build a house, and someone's like, oh, what are you going to build the house out of? I don't know. Maybe brick, maybe wood, who knows? But I'm like having trouble building it. Well, like, yeah, you can't build the house until you've decided what you're building the house out of, right? It's the same thing here. You cannot build your equations until you know the building blocks that are going to go into your equations. And sometimes students will be like, oh yeah, I didn't write them down, but I know what my variables are. Don't do that, right? The more stuff you're holding in your head, the more confused you're going to be. Write it down on a piece of paper, and now your brain doesn't have to hold on to that information because it's on the page, and you will make less mistakes. Mistakes take forever, right? Because you spend time working on a problem that's already a mess because you've made a mistake. You just don't know it yet. You get to the end, you make a mistake, which on Delta Math, if you make a mistake, you now have to do another problem. But then you have to go back and try to find your mistake. That takes forever, right? So, you know, go slow to go fast. Do it right the first time, and you won't have to spend time redoing it. So, right, I get in these problems where the whole point is to write the variables down. But even when you get to the problems that just say solve this system of equations, write it down. Okay, write the thing down. So in this case, you can choose X and Y. A lot of times we use X and Y for variables, but sometimes you can choose better variables that are remind you of what it is, right? So if I'm doing a a systems of equations where it's about a car and a truck driving away at a certain speed, well, then maybe the variables that I would use would be C and T for car and truck, because then I'm not going to mix them up, right? A lot of times, like, I'll see students, they do the system of equations right, but then they answer it backwards. They mix up the two variables, and then sometimes there's this attitude like, oh, well, all I did was mix it up. But it's wrong, right? If you're at your work and they need to know how many of part A and how many of part B to buy next month, and you get the values right, but you mix them up and your company orders the wrong parts, nobody's going to care that, like, oh, well, my math was right. I just mixed the parts up at the end. No one's going to care. You just screwed up the business, right? So it's really important that you got to get it right from beginning to end. So you can choose X and Y. I think for here, I'm going to choose A and B because there's drink A and there's drink B. So if I choose A and B, I'm not going to accidentally mix them up, right? This is part of choosing smart variables. So A is one variable and B is another variable. And then it gives us a drop-down box. Sometimes people go like, oh, A is drink A and B is drink B. But that doesn't really make sense because A is a variable. It represents a quantity. Right? It's not literally a drink. You're not going to hand someone the letter A and then they drink it. A is a variable that holds a quantity of something. So you can't just say it's drink A. What is the quantity that you're after? So it really helps to write out the whole thing. So A could be the total liters of fruity drink made, the total liters of real fruit juice needed, the amount of real fruit juice in each liter of drink A, the amount of real fruit juice in each liter of drink B, the number of liters of drink A made, and the number of liters. Oh, I should scroll down a little. Oh, here's our choices of drink B made. Now, honestly, I can't answer this because we've been talking and I've forgotten what the problem was about. So remember I talked about reading it until you understand it? 2 minutes later, you might find yourself forgetting. So what do? Read it again. So let's see. Let's go back. What do we want? Okay, so we're given, we've given the total amount of real fruit juice. One of these is 30 more than the other. We want to determine the number of liters of drink A made and the number. Okay, so we're determining the amount made of each one. See how it's not enough to say like drink A and drink B. Well, is that the amount of real fruit juice in drink A, or is it the number of liters of drink A? Those are different. So be specific with your variable, or once you confuse yourself, it's really hard to get through the problem. You almost have to start over. So let's see. We are going to choose the number of liters of drink A made, and I'm going to choose the number of liters of drink B made. That, I believe, is going to get us what we need here. Now I have to write the system of equations. Well, for many of these, there's oftentimes an equation that's a little trickier to get your hands on, and then there's one that's sometimes a little bit easier. So they tell us here, they actually kind of were kind of sly. They're giving us information in a way where we really have to slow down and think about what that information is. The company used 100.5 liters of real fruit juice to make 30 more liters of drink A than liters of drink B. Okay, so what does that mean? Because I see students do this one backwards all the time. So slow down and think your way through it rather than do this part backwards. So there's 30 more liters of drink A. So that means if I've got my vat of drink A, there's 30 more liters in it than the one for B. So one of our equations should say is that A is equal to B plus 30. Okay, 30 more liters of drink A. And some people go, well, wouldn't 30 more liters of drink A say that A plus 30 equals B? And the answer is no, you have to be careful. There's 30 more liters of drink A, so that means we have to add 30 to B to make it equal A. Right? So there's usually hidden in these problems, there's an equation that equates the total of amounts of the things. Okay? In this case, they made it that one was 30 more than the other. Okay. Now is the one that's a little bit trickier. So we know that the company used 105 liters of real fruit juice. Okay, so how could we get our hands on that? Well, I know that drink A is 20% real fruit juice, and I have a way of representing the amount of drink A. It's A. So if I take 0.2, which is 20%, 0.2 times A, that should give me the amount of real fruit juice that's in drink A. And if I take 0.15, 15%, times B, that should tell me the number of liters that were used in the drink B. And if I combine those together, that should give me the total 100.5 liters. So let's try that. So we've got 0.2A plus 0.15B equals 100.5. Submit my answer. It says, are you really sure about all this? Yeah. And there we go. Got it right. Okay, so define your variables. Very important. Don't just say A is drink A and B is drink B. That's sloppy, and it's sloppy in a way that's actually going to hurt you, right? I know sometimes people view that, as teachers, as we do a certain thing, they're like, oh, you're kind of overboard with making me write it this way. But saying A is drink A doesn't really tell you anything. Is it the color of drink A? Is it the amount? Is it the sugar content? Like, what are we talking about? This one makes it very clear. Oh, this is the number of liters of drink A that were made. Very clear what's going on. Then you have to search through these and pull out the information and convert it to an equation. Now, there's two things about that. One, there's no shortcuts for critical thinking, right? You just have to practice these. But that's the other piece. The good news is, after you've done like 3, 4, 5 of these, you're going to get it. It's like something's going to click and you're going to go, I see how these work. And you're going to be able to work through them in a more reasonable way. Okay? So you've got your equations. And then as of yet, we're not even solving a system of equations. We're just figuring out how to set them up, right? And in some ways, you could argue this is more important because there's software now that solves systems of equations. Like I mentioned, when I was in grad school, I mean, we were using high-level like engineering and math software to run calculations on systems of equations. But right now, you can find apps and free websites and stuff that will solve small systems of equations for you. They can't do one that's like 30 variables and 30 equations because it'll bog down their server. But for simple basic systems of equations, you can get those solved. But here's the thing. The app can't create the systems of equations for you. So the problem we just did, an app can't do that, right? It can solve your system, can't do this. Can't do it. So that's kind of the future of math, is not just doing calculations, but being able to make use of it, right? Being able to go to your boss and say, yes, next month we need 500,000 of part A and we need 750,000 of part B. That's what we need for next month's production targets. And they go, okay. They don't care what you did along the way as far as your math scratch work. They just want to know, do you have a conclusion for me? Yes. This is what we should buy for these parts. Okay, great, do it. Right? Or, we'll be spending all sorts of time on dosages later in the class. So we'll go over all that, okay? But your conclusions and your setting up of the problem, apps can't do that for you. You need to know how to do that. You need to understand that part. Okay? So we've got that. That's the setting those up. Okay, then we start getting into solving systems. How do we go about solving the system? We looked at one way where it's graphical solving, but then we kind of said like, yeah, that way has some problems because we get very inexact answers, and we don't want inexact answers. When someone wants a certain amount of medicine, they need to get the right amount of medicine, right? If you give someone too little medicine, then you're not going to accomplish the goal of giving them the medicine, whether that's pain relief or, attacking something in their, a bacteria in their body or whatever. You need the right amount of medicine. But if you over-medicate, it doesn't take too much imagination to figure out how that can go poorly as well. So when we're calculating things, it's important that we get it right, that we do the right amount, and not we don't want to be lazy about it, because there's consequences, especially for for many of you. Like, we're talking about serious stuff about getting the math right. So what do we do? How do we solve systems of equations exactly? And in that case, we need algebraic methods. So then we have two methods for this, and the first is called substitution. And there's good videos, both that I've posted on the website, but also in all over YouTube. There's all sorts of stuff. I mean, you can find so many videos for systems of equations. They're, as you remember, built into the homework problems. So watch those. There's two methods, and you might go, why two methods? And I get that, because as a math teacher, I don't like to teach people 5 different ways to do something. It's like, just teach them one way, and then make them work on that till they get it, and then they can solve that. Because most math problems have numerous ways to be done. But why do we mess around with 2 ways for systems of equations then? And it's because there are certain systems of equations that are much easier to solve with this first method, substitution, and there are some systems of equations that are easier to solve with elimination, which is the other one, the other method. So you could solve every system of equation out there with substitution, but you're oftentimes going to end up doing way, way more work than you need to in order to get to that point. Okay? You could solve every systems of equations by elimination, but again, you're going to frequently do more work than you need to do in order to get it done. That's why we have 2 methods. So the first one is called substitution. Let's take a look. Substitution level 1. They're kind of making it too easy here at the beginning. Let me show you a more complicated one. Okay, we're going to look at this one. Yeah, let's do this one. So negative 7x minus 2y equals negative 38. So, oops. Negative 7x, what was it? Equals negative 38. What was it? Negative 7x minus 2y. Minus 2y. Negative 7x minus 2y equals negative 38. And then negative 3y equals x. Negative 3y equals x. This is one of those sections where I highly recommend, when you write down the problem on a piece of paper, take an extra 2 seconds to just double check you did it right. A significant portion of the time when we're doing systems of equations in class and someone calls me over and says, I don't know why it's not coming out right. I swear I'm doing it right. And we look and go, oh, you got the wrong sign on this problem at the beginning. You did your work correctly. You just did the wrong problem. So take an extra second or 2 to double check that it's right. And you see me doing that, right? Because I don't like wasting my time on a problem that isn't coming out right. Because it's the wrong problem. Okay. So substitution, what do we do? Step 1, you solve for one of the variables in one of the equations. We already have that. See how this x is all isolated all by itself? It is solved for that variable. Now, you might say, well, isn't this one solved for too? No, because it's not y equals. It's negative 3y equals. We want to have the variable all by itself. You could solve it for y if you wanted. The problem is if we solve for y, we're going to get fractions. And fractions are fine, except I don't want to deal with them, right? If I have the choice between doing a problem with fractions or doing a problem without fractions, I can do both, but I'd rather do the one without fractions in it, right? So we're going to use this substitution right here. We have this equation to solve for this variable. Now, most of the time, you have to get it to that point. You have to get it where it's solved for that variable. It just so happens in this problem, it's already been given to us, okay? Then what you're going to do is you're going to make that substitution in the other equation. You have to use the other equation. So we're choosing to use number 2 as our substitution. That means the equation we substitute into has to be the other one, equation 1. So what does that look like? Well, that means that instead of writing x, I'm going to write what x is equal to, which is negative 3y. Okay, so if you look at the first equation, if I turn that x into a negative 3y, then it looks like this. Negative 7 times negative 3y minus 2y equals negative 38. see, did I get this right? That looks right. Yeah. Okay. So then we just go through, okay, what does this give us? -7 times -3 is +21. Hopefully I didn't make a mistake already. It's starting to look like a little weird, but maybe it's right. 21y minus, oh no, I think this is right. 2y equals -38. Okay. So see what I did? You see how the thing in the parentheses, I've just changed this x from the original problem into what this equation says x is equal to. So instead of x, I wrote -3y. That's the substitution piece. You're substituting something for something else. Just like you could do in a recipe, right? You're like, I don't have regular sugar, but I have brown sugar. Okay, well then you can substitute it in there, and sometimes there's a ratio. You have to change it a little bit, but that's the substitution you make. We're substituting right here. So this will become, when I simplify this, this becomes 19y equals -38, and then I divide by 19 on both sides, and I get that y equals -2. Okay, great. That's awesome. Sometimes people think we're done here. There's a tendency to go, well, I solved for the variable. What's the problem? Well, let's go back to our system here that we solved graphically. What do we know about the solution to this system of equations? It has two parts to it. It has an x value and it has a y value. If you only have that, you've only done half the problem. It's not very helpful, right? It'd be like, you know, like one of the problems we solve with systems of equations in the business class is like we're maximizing profit. Well, if you don't know both of those variables, you don't know what you need to know. It'd be like going into your boss's office and he's like, okay, or he or she is like, okay, have you figured out how many units we need to sell next month to maximize profit? And you go, no, I don't know how many we need to sell, but I know if we maximize profit, it's going to be $500,000. That's usually the Y value. And he's like, well, he or she is like, that's great, but like, we need to know how many parts to sell in order to make that work, right? So you need the X value as well. You need both parts of that solution. So it turns out we are only half done now that we got the y equals -2. We have one of our two variables solved for. So we have to go back and get the other one. But the good news is we've actually done most of the work. We only have half the solution, but we've done more than half of the work. Because now what you're going to do is go back to your original system of equations, and you're going to take whichever one looks easier to you. In my case, I think number 2 looks a little bit easier. So I'm going to use this second equation right here. Why is it highlighting all that other stuff? I'm going to use this second equation right there, and I'm going to plug y equals -2 into this equation. So when I do that, I get, so I have my -3 from the problem, and then y is -2, and that equals x. See, it's this equation, except we've turned the y into -2 because we learned that y was equal to -2. So that tells us, oh, it looks like x equals 6. Now, here's the thing about systems of equations. They're easier to check than they are to solve, which is nice, because it can be tricky to find the solution, but once you have the solution, it's easy to check. You want to plug the x and y into the original equations. Now, with Delta Math, I highly encourage you to do this, because when you get one wrong, you have to do a whole new problem again to get that score back, right? If you check it ahead of time, you'll just get them right every time. Doesn't that sound good? I could get the problem right every time? Yeah, you just have to check it before you put it in there. So how do you do that? Well, you take an x value of 6 and a y value of -2, and you plug it into both of your original equations. So let's see, if I do that, I'm going to get -42 plus 4 equals -38. Yeah, that's right. Okay, now I'm going to plug in 6 and -2 here. So that's +6 equals +6. Yeah. It works in both equations. Now, some people try to shortcut it and go, well, can't I just check it in one? If it works in one, isn't it likely that it works in both? And the answer is no. Because if we made our mistake right here at the end, then the solution will satisfy one of the equations, but it won't satisfy the other. So you really want to check both. It's really in your best interest, and really it's like the easiest part of the problem. So it's better to do the easiest part of the problem rather than have to do a whole nother problem, right? So let's see, where are we? Right, so our solution should be 6, -2. So let's go back over here. Okay, and they even have it in the form of a point for us, right? So we said what? 6, -2, submit. Yep, there it is. And you can see they're basically doing the same thing. So they did this. They used this as their substitution. See how the x is blue in both? They turned the blue x into the -3y. That's exactly what we did. Right? That's exactly what we did. Solved it, got y equals -2, went back, got x equals 6, and then there you go. Some people get confused about the ordering. They're like, oh, well, I got this one first, so isn't that the x? Pay attention to your variables. It goes x first, then y. So if you solve for the y first, that's okay. Just recognize that's the second one in your coordinate system there, okay? So we've got the 0.6, -2, and then you just go on to the next one, and now they have another one, substitution. But that's what you're going to do every time, is you solve one of the equations for one of the variables. You make the substitution into the other equation, the one that you didn't use to get your substitution. You use the substitution in the other equation. You solve for one variable, and then you solve for the other. So I think you'll kind of get it. We're kind of running out of time. I'll see where we are next week. I don't know if I'll be able to cover elimination, but I think it'll make sense from the videos. I think you'll probably get what you need. So if you're having trouble, the tutoring center can totally help you with this. I can help you with this in office hours. All sorts of stuff we can do. So make sure you're getting help. And the good news is that elimination method, I'll talk about it for a little bit with the time left. I don't know. We don't have a ton of time. But the elimination method, the second half, is just like the second half of substitution. So in both of these methods, remember how we got one variable, and then once we had one, we just plugged it in back up here and got the second variable? That's how the second half of elimination works too. Okay, it works that same way. The only difference is in the beginning, setting up the beginning of the problem. So I talked about how sometimes it's beneficial to use substitution, and sometimes it's beneficial to use elimination. So how do you tell the difference? If one of the variables in your original equations has a 1 or -1 as the coefficient, then substitution is usually easier. Like for this, see how we had an x here? That's like 1x. Then that means substitution is going to be easier to do. If you have a situation where none of your variables have a 1 or -1 on them, then more than likely when you start trying to use substitution, you're going to introduce fractions into the problem. And once you introduce fractions into the problem becomes less fun to do, right? I think we can probably all agree on that, I'd rather do a problem with no fractions than one with some in it. We don't have to be afraid of fractions. We don't have to let them like psych us out or think we can't do it. But, we don't want to do more work than we need to, right? We don't want to do an unnecessary amount of work. So let's see. Let's go back because there was these solve systems of equations from context. These are basically word problems. You're gonna read this. You're gonna create a system of equations. You're gonna solve it, and then you're gonna answer the question. So it's just a matter of doing enough of these that it makes sense while you do it. Okay, so what's elimination look like? I'm actually going to show you, because I'm short on time, I'm going to show you the solutions to one, and then we're going to look at that. Wait, where did my... Oh, did I just close Delta Math on accident? Let's see. I think I clicked the wrong button maybe if I go back here. And let's see, where do I want to go? I'm going to go in here, simple student page, Mondays, where were we? Right, let's look at elimination. Oops, that was equivalent systems. Oh, there's 3 types of solutions. I should mention that before we break as well. Let's see, okay, elimination. I just want to go to the solution. Okay, so see how this systems of equations does not have a coefficient of 1 or -1 on it? That means that, like, up here, if we were to divide by one of these coefficients in order to solve for that variable, we'd end up with fractions. The same down here. I guess you could divide this one by 2 and get away with it. But usually if you divide by one of the coefficients down here, you're going to end up with fractions. So what you do then is we take a different approach. We try to get one of these variables to cancel out. So see how you have a -2y in this equation and a +2y in this equation? Well, -2y plus 2y gives us 0. So what we do is we literally add the equations themselves together. And this like sometimes confuses people a little bit. We're used to adding terms together. Now we're actually adding equations together. But that's okay, right? So you add up your x's. 5x plus 6x is 11x. -2y plus 2y, all the y's cancel. That was the whole point. And then we add these together to get 11x equals 44, x equals 4. And from this point on, it's just like substitution. You go back to an original equation, you plug in x equals 4, and you get that y is 4 as well in this case. And you get it that way. Okay? So what happens, though, is in this case, the y's were already ready to be added together. Usually that's not going to happen. Usually you have to do some work to get them like that. So let's look at this one. Here we go. See how none of these variables are ready to cancel each other out? So what you have to do is find a number that you can multiply the equations by that's going to make one of those variables cancel out. So you might say, well, I have a +4y in the second equation, so why don't I multiply this first equation by 2, and then I'd have a -4y in the first equation, and then when I add them together, I'd get 0, right? I'm betting that's what they do in their solution. Yeah. So they took the entire first equation, multiplied by 2, and now they have the -4y up here. Well, when I add those together, they cancel. So that's part of your decision when you're looking at it. You go, which variable do I want to get rid of? And honestly, it doesn't make any difference. It doesn't matter which one you get rid of. But just decide on one, and then go, what do I have to multiply these equations by to get one of those variables to cancel? You do that. Then you end up with one equation and one variable. You solve it, and you're good to go. Okay, real quick, I want to show you something here on Desmos. So this is what you get most of the time. You know, something like this. You have a system of equations. We get that intersection point. We said that intersection point is the solution, and you find that solution algebraically, and you're good to go. But occasionally, you get these kind of weird answers. So what if we had this problem? So what about this? These are two parallel lines. There is no point of intersection. So wait a minute, we're trying to find the solution, and we said the solution is the point of intersection, but parallel lines don't have an intersection, so the logical conclusion is that this system of equations has no solution. There is no solution. This can't be solved. You can't, and that's disappointing sometimes when you're trying to figure out something and you realize there's no way. That basically means there's no way to make this work. Whatever it is you're trying to do with your research or your business or whatever, it's not going to happen because there's no solution to that. So parallel lines give us a no solution. So you should picture this in your brain when you're getting it. No solution, parallel lines, because there's no point of intersection. The way this looks when you're solving it algebraically is you sometimes will get to a point where you get an equation like 0 equals 4, where your variables are totally gone, but what you're left with is a false statement. Well, when does 0 equal 4? right? It sounds like a joke, but it's not. When does 0 equal 4? Never. 0 never equals 4. It equals 0. So if we get to something like 0 equals 4, then there must be no solution because that cannot exist. That cannot happen. So you throw it out. 0 equals 4. Nope, no solution. Get rid of it. The other scenario is when you see something like this. So look at that. On the left, it looks like two different equations, right? And I could mix them up even more. Some of you might recognize, well, the second equation is just the first one multiplied by 2. But we could mix it up differently, and you wouldn't recognize that they're the same thing. So what we really have is the same line represented twice. And this seems like a silly scenario where you're like, why did you build your system with the same line twice? Well, usually it doesn't happen on purpose, or it happens in more complicated ways where there's actually a good reason to it. But the bottom line is, what we need to know for now is that this causes the same line to be written in two different ways. So what are the points of intersection? Well, there's an infinite number of points of intersection. So there's an infinite number of solutions. Every point on the line is a solution. They're all solutions, right? So you'll see when you're doing the homework, they'll show you how to write the solution for that, how to write the answer. But that's the idea, is you usually get, your lines cross at one point, that's your solution. Your lines are parallel, so there's no solution, or your lines are right on top of each other and you have an infinite number of solutions. Those are the only three outcomes for a system of equations, at least two variables and two equations. Okay, so that's how those work. So just to remind you what we've been doing in class, please go do the graded class discussion. I see some people are already getting in there and getting it done. That's great. Be one of those people that gets in there and gets it done. You have more time, but why wait, right? The only thing that can happen, like, think of it from a game theory perspective, right? What is the benefit of waiting? Nothing. What is the risk of waiting? Well, you might end up with a 0 because you don't get turned in on time. So go in there, join the class discussion, get your easy 10 points, and we'll go from there. We will continue talking about this kind of stuff. Right, this is the online class, so we won't be meeting ever in a classroom. So that's where we're at with that stuff. Feel free to send me questions. If you have don't just say, oh, I don't get rational equations, but like if you have a homework problem that you need me to go over, or you want me to go over, I can do that. But specifically send me which problem it is, right? Don't just say, oh, it's a problem from this homework. Like you can screenshot it is helpful, or you can tell me specifically, like, you know how they say, like, I also have students that tell me, like, oh, can you do a problem from substitution level 3? And then all I have to do is click it and go, yeah, I'll do this in class. I'll go over this one right here. But you got to be specific, okay? So if you need to see a specific type of problem, let me know. Maybe I'll go over to next week in class. Otherwise, we'll keep moving ahead. Thanks, everybody. So I'm going to close down the Zoom meeting, the YouTube stream. Anyone who wants to talk to me, stay in Zoom. Otherwise, keep up the good work, and I will see you next week. Okay? Thanks, everybody.